Method 2 class, the 8th edition. And I hope that you had a blessed weekend. And I also hope that you are full of strength and energy to go through this week, because the week will be full of hard work and challenges. So I wish you a very good week. All right, so remember last time we tackled the continuous fraction expression or representation of a real number. And the motivation of continuous fraction is for us to be able to represent a rational function in a simplest form, to reduce the number of floating point operations, particularly the number of multiplication. So that is the motivation for us to go through this continuous fraction. So in terms of continuous fraction, we saw that in order to represent a real number using continuous fraction, if the real number we want to represent is a rational number. Rational number means that it's either an integer or rational, because remember that the set of integer is a subset of rational. So any integer is a rational number, right? So if you have a rational number, then this is one of the way you can represent it. A0 is just an integer. It can be positive, it can be negative. It is negative if and only if the corresponding rational number is also negative, and positive is the corresponding rational number is positive. Okay, now in the expansion, in order to expand this, we follow a certain algorithm. And we say that the algorithm that we follow goes as follows. First of all, you take your rational number, which, the real number, R. You split it into two parts. You have the integer part and you have the fractional part. And the rational part is any number after the decimal dot, the decimal dot. The decimal dot gives you the rational number, or the rational part, right? Rational part. And the integer part is the term to the term on the left of the dot. Let's say 2.5. 2 is the integer part, and 0.5 is the fractional part. So once you have it, you keep the integer part. Now the rational part, you take its reciprocal, and then it gives you a new real number. And to this new real number, you repeat the above process, meaning you split that real number into integer, rational part, fractional part. And to the fractional part, you take the reciprocal, which you denote by a new number, and you repeat. So you proceed this way until the rational part or the fractional part becomes 0. When the fractional part is 0, you stop the process and you collect all the previous the integer part, yeah. In that order, it will give you the sequence that will represent your continuous fraction. You see, okay, for the first time, A0 will be your first integer part, right? And A1 will be the second one obtained through the fractional part, and so forth. As an example, if you take 9, 7, right? 97 can be written as this: 1 and 27. 1 and 27, meaning that you just add 1 plus 27, it will give you 97. So if you look at this expression, you can see that your real part is 1 and the fractional part is 27. So you draw this table where the first column will represent the real number, the second column will represent the integer part, because you split your real number into its integer part and the fractional part each time. So we take this first real number, we split it into its integer part, which is 1, and the fractional part, which is 27. And then another column for the reciprocal of the rational part. So this reciprocal is the reciprocal of the fractional part. So that reciprocal is a new, in fact, the current entry in the column of the reciprocal of the previous fractional part gives rise to a new real number, which will go to the next row in the first column. First column representing the real number part, right? Or the real number, the column for real numbers, right? So this 3 1/2 goes there because this is a real number, which you can split again into integer part, fractional part. So we have 3 1/2. Now, if we take the rational part, the reciprocal of this fractional part, it will be 2. So you see that when it's 2, you can see that the fractional part is 0. So you take this, that's your new rational number, you write is integer part, which is 2, and fractional part, which is 0. So once the fractional part is 0, you stop the process and you collect all the entries in the integer part. So you can see we have 1, 3, 2. So this is A0, A1, A2. A0, which is 1, A2, A1, which is 3, A2, which is 2. So this is a sequence. So you write the representation of the continuous fraction representation of your number in this form as a sequence of A0, A1 up to AN, which you can write equivalently in the following form. So this is A0 plus 1 by, you see that this is a fractional part. This one, 1 by, what is it? This one is 1 by 2. Sorry, 2 by 7. This one, 2 by 7. And then the reciprocal is what we have here. Right. That this is 1 by F. This is F, which you break again into 2 parts, the integer part, fractional part, and you write in that form. So for those who were not there last time, I told them that what was written here in the denominator was wrong. I corrected it last year, but I did not update on the 5. So that's why you still had 1 plus 1. No, the last number, you count the number here under the, in this integer part, the column representing the integer part. We have 1, 2, 3 terms. 1, 2, 3 terms, and those are the A0, A1, A2. So the last AN is in the denominator, and it should appear exactly the way it is in the column 2. So 2 should appear here. You don't have to break that into ones. No, that last number should be the last in the denominator exactly the way it is defined here. You can see that you have 1, which is A0, 2, which is A1, and 2, the last one, A2. So you can see that A2 is written as it is. You don't need to break it into another form. You take it as it is and put it there, substitute A2 there. Similarly, if you have 4 terms, A3 will be the last term in the denominator. So that's what I did here. It should be 2, not 1 plus 1 by 1. No, it should be 2, exactly the way they appear here or in the column. 1, 3, 2. So you should see 1, 3, 2. 2 being the last integer part, that will be the last number in the denominator. 2. Right. Similarly, the second example, this one, we proceed in the same manner, and we stop once the fractional part is 0, and then we collect this sequence 3, 4, 12, 4, which you can see here, 3, 4, 12, 4. So meaning that you write A0, A1, A2, and A3 in the denominator, and A3 is 4, so 4 should be here. You don't break it the way it was written there, 3 plus, no, that's wrong. It should be 4 here in the denominator. And all these the element here in the sequence are the 1. That will be our A0, A1, A2, up to AN. And AN is this last number, which is A4 in our case. And that AN is in the denominator. You don't break it, you leave it as it is. Good, I hope it's clear for everyone. So that's what we did last time. And I asked you to try to read continuous fraction, apply now to rational, because what we did here was we applied to real numbers for you to understand the procedure, how to represent. Now, in terms of rational number, for a real number, the A's are integers. Okay, so when you write the sequence, A0, A1, A2, up to AN, the last one, all these AIs are integers. All of them. Okay, this is something that is good to bear in mind. These are all integers. The first one is positive or negative. Positive if the real number is positive. So if R, the real number, is positive, this implies that A0 is also positive, right? Or 0, positive or 0. Okay, now if R is negative, A0 will be negative also. But the remaining so be it for the first or the second part, you have the same thing. So except A0, from A1 up to AN, they are all positive. And the first A0, the first term in the sequence, A0 can be positive or negative, right? Depending on whether R is positive or negative, right? But the remaining terms of the sequence are always positive, always. Because let's see, if you write 2.15, if you split that into 2, for the integer part, which is negative 2, and now you can see that the fractional part is always positive. You see that this is always positive, always positive. But this can be negative or positive, depending on whether the real number itself is positive or negative. You see? So that's what I mean by this. Okay, so the most important thing is to realize that your AIs are integers. Now, when it comes to this one, for rational function, if you want to also write the continuous fraction of this, it will be of the form okay. Now I will write P. This one will be like our P0, which we can write as okay. Let me write it P0x here plus 1 by P1x plus 1 by now here we have P2x plus 1 by, so it will continue like that until maybe, let's say, if we stop at P3, this is what we have. So the last denominator here is a polynomial like this one. But what are these polynomials? Each pi is a polynomial of degree less than or equal to one. Polynomial of degree less than or equal to 1. 1, meaning that pi x can be written as aix plus bi. You see, it has to be of this form, where ai and bi are real numbers. You see, this is very important to note. Here our AIs are integers, right? And the AIs are the terms of the sequence here. Similarly, the terms of our sequence, when we are dealing with a rational function, we call them P0, P1 up to Pn. And these P's are of this form. Oh, sorry, this is AX, not A of X, AX. That is A times X, first degree polynomial. So this okay, so it's AI times X. So it's a first degree polynomial. First degree polynomial. Okay, so this being said, let us now tackle the continuous fraction of a rational function. So this is the first example. Rx is equal to 3x squared minus 4 by x minus 1 squared. Now we can expand the numerator, we get this, right? So you can see that this is a second degree polynomial, the other one is a second degree polynomial. So if you perform the long division of this one, we'll get a constant term here. So we can split this and it will be a certain constant term plus a rational function, where the degree of the numerator will be less than the degree of the denominator. So if you perform that continuous fraction, long division, this is the long division, we can rewrite this as 3 plus this last term by this, which is 3 plus that. So this is the constant term I'm talking about. Because they have the same degree, if you divide this by that, you first have a constant term plus a rational function where the degree of the numerator is less than the one of the denominator, because currently they are equal. Now you can see that by performing the long division, the numerator of this rational function, the new one obtained here, you can see that the degree of the numerator is 1, whereas the one of the denominator is 2. So when you perform the fractional, the continuous fraction, first make sure that you obtain an expression here, surely a polynomial, and that this will be your P0x, and then the remaining term here, or the remaining expression here, make sure that the degree of the numerator is less than that of the denominator. Then you take the reciprocal. Remember, this now is like our integer part. This is like our integer part, because remember, this is a polynomial, whereas this is a fractional, a rational function. Here you have a polynomial, this is a rational function. So this is polynomial. Polynomial is exactly the way when you write your R as integer dot fractional part. You see that the integer part is an integer. It's not a fraction. So it's exactly the same way. If you have a rational function, you can always write it, first of all, as a polynomial, which is like your integer part, plus, now you have a fractional part, because this is a fraction. That's why we call it fractional part. It's a fraction. The degree of the numerator is less than the one of the denominator. So this is a fraction. So this is like the real part, this is the fractional part. The real part corresponds to the polynomial, and the fractional part corresponds to what? Rational function. Now you take the reciprocal, that's what we are having here now, right? 1 by this. So 1 by this not necessarily exactly that way, but we write it as 1 by something, right? Right. This is like 1 by, because by doing this, this becomes this one in the denominator. When you write this as 1 by the reciprocal of this, right? 1 by the reciprocal is this one, gives you the expression. Now, to this expression, you can see that the degree of the numerator is greater than or equal of that of the denominator. You can perform another expansion of this one where you have your integer part, fractional part, or polynomial plus fractional part. See, if we perform the long division to this one, you will see that another integer part or another polynomial will be generated. So you can see that the difference, what the constant term here, or that integer part will be what? The degree of the numerator minus the degree of the denominator. So it will be a first degree polynomial that will appear here as our P1. So if we perform that, we can see that this okay, so now if you perform the long division, to this expression, you see the denominator now, you can see that it can be written in this form. This is your first degree polynomial I was talking about, which is like your integer part. It's a polynomial, first degree polynomial. So this is your P1. Now, this is your rational part, because you can see that this is a fraction. Right? The degree of the numerator is less than that of the denominator. So if you rewrite the expression, you still have your P0 here. This is your P1. You can see that this is a polynomial of first degree, right? Plus, you have this expression. This, you can stop here because this is already a polynomial, so you can stop. So this is your P0. This is your P1. and this is your P2, and you stop there. So Rx written this way, this is your continuous fraction form. Obviously, this, you can take the 36 in the denominator, it doesn't change anything. But maybe for simplification, that's why we wrote 1 by 36, right? Because remember, it's always 1 by something. But you can keep this as a fraction. It doesn't matter. The most important thing is that you show that here you have a polynomial and here you have a real number, right? So that is it for, once you understand continuous fraction for real number, that's exactly the same thing you apply to rational function. The philosophy is exactly the same, right? Okay. Okay, please go through this and make sure that you can perform these divisions and express all the terms this way. Right. Okay, now the homework that I'm giving you, please go and perform the long division to this expression and make sure that you can obtain this continuous fraction representation of Rx, this one. And this is the Padé approximation of exponential x, right? The fifth degree, you can see 3 plus 2, fifth. So this is a fifth degree Padé approximation of exponential function. And this, in fact, is R. This is also, we could have called this R 3, 2x, right? Where 3 is the degree of the numerator and 2 is the degree of the denominator. So normally this is how you are supposed to write it. And to get a degree of this rational function, you just add these two indices. 3 plus 2 is 5. So it's the fifth degree where we decide to take the numerator, the degree of the numerator 3, and the degree of the denominator 2. Right. So please perform the continuous fraction to this and make sure that this is what you obtain. This expression. Okay, so this is a homework. I ask you to submit. It will be your first homework. Submit this. Submit this homework. You have to Friday. Till Friday. You have till Friday to submit this work. Homework number 1. This is the first homework. Deadline. The due date is Friday. Friday. What is the day? When is Friday? Is the? It should be the 4th, right? Well, let me check. Friday should be no, the 3rd. Tomorrow is the 31st, if I'm not mistaken. Then we have Friday is the 3rd, exactly. Friday is the 3rd. So due date for submission. So this exercise, homework 1. Due date Friday, 3rd September. By what time? Send me the email by 6 p.m. Please write it down. Is that clear for everybody? So far, so good. Any question, any concern? Class rep, you have been absent, eh? You have been absent, you have been absent. There's no more will. Nanuna. Class red. Apparently she just logged in and she disappeared. Nanuna, are you there? You see, she's not around. That's how I discovered those who are present or those who are not. So you can see that the class rep is not there. Kashopi, can you say something to make sure that I'm connected? Because I see. Yeah. You see. She can talk, but
having technical issues.
Sorry?
Nanona has technical issues.
And how do you know it?
I'm on a phone call with her, sir.
All right. Okay. This being said, let us proceed with our program. Chebyshev polynomials. Hey guys, we are here to do math, ne? All right, we proceed. If somebody is absent, the person might bite the dust. Anyway, we proceed. Please don't be confused when it comes to this Chebyshev polynomial. Remember what we did. It's not that different from the least square method, right? It's not that different. It's not different because what we are going to do here in this section 1.7, it is similar to the least square approximation. Remember that least square approximation we perform when you say you fit a polynomial, degree 1, that's straight line, degree 2, and so forth. This is the form of the function that you try to fit to the set of data points. So the objective is to determine the coefficient here, this Ci, this one, Ci. That's what you try to determine. When you fit a polynomial, for a polynomial, all these, the basis, the g's, this one, this basis, which you choose to be linearly independent, don't forget that when gx is a polynomial of degree x, a polynomial of degree n, this g, all this g sub I x is x to the I. So G0 will be 1, G1 will be x, G2 will be x squared up to Gn will be x to the n. And you see that this polynomial, Pn, which is your Gx here, will be written as an, okay, this one, see, I can write this as sum AIXI. So by identification, we can see that the AIs correspond to what? Ci, right? And Xi correspond to Gi. I want you to understand this clearly, because that's what we are going to generalize here. So the form you want to fit to your set of data points can be written in this form. A polynomial falls into that form. And that's what I'm trying to explain here. So you can use a polynomial, you can also use trigonometric function, which we also call trigonometric polynomial. Right? For instance, if you take another form, if you take Okay, if you take this type of basis, right, you can also take the basis of the following form. You can take this basis in the following form. I mean, when I say GI like this, there will be two parts, right? There will be two parts. I can take this to represent sine or cosine or both sine and cosine. I'm just trying to think how I can do that. But you can always do this. You can use your basis, this one. You can take this basis to be, you can choose this basis. You can split that to be, okay, I'll write it here. In that case, you get trigonometric polynomials, right? So you can take this basis, you can split that basis into a constant term, which I can call 1 for the constant term. Now the remaining one, you can have sine x, sine 2x, all the way up to sine nx. You see, then you have all these terms. But or instead of sine, you can replace sine with cosine. You can. Okay. I will not. There's a problem. Okay, so you can represent the sine with cosine. All right. Right? Or you can take both. Instead of sine only or cosine only, we can mix sine and cosine. So you first take the sines, sine x, sine 2x up to nx. And then cosine x, cosine 2x up to cosine nx. You can write it this way, or you can alternate here. That is sine x, cosine x, sine 2x, cosine, doesn't matter. You can still group the way you want. So this basis, please, I want you to listen carefully. I want you to listen carefully, because what I'm explaining here is exactly what we'll be doing later on with Fourier series, right? I want you to understand that very clearly at this stage. I want you to understand. And these are bases, right? Because we want them to be linearly independent. These are linearly independent. All these, they are linearly independent. They are linearly independent. So you can choose this basis to be one of these and substitute into this representation. Oh, and substitute that into this. Right. Okay. This being said, I hope it is clear for everyone. So the purpose is to select a basis and then expand the function we want to set to fit to the set of data point in this form. Write it as a linear combination of the element of the basis. Once you have it, then you determine the coefficient here, the CIs. Because remember that the normal equation is the equation that will allow you to determine the constant here, the constant term. And the normal equation is when you apply the least square, right? Okay, so this is a generalization of the least square method. Generalization of the least square method. Now, Chebyshev polynomial would just be a particular form of a basis here that we can use to fit our data point. Let's say, for instance, if we take this basis to be Chebyshev polynomial, our least square approximation will be simplified. Why am I saying that it will be simplified? We are going to do it. We are going to do that very soon. And you will see why the choice of Chebyshev will simplify our normal equation. Because normal equation, if you recall, all the method that we perform, we obtain a normal equation, and the unknown in your normal equation, the determination of the unknown consists of solving a linear system, right? It consists of solving a linear system. As you can see, for instance, for this case, it's a linear system that we are solving. Similarly, here is a linear system, right? This is a linear system. I already explained why this is a linear system. I show you that you can write this in a matrix form. So this is a linear system we are solving. This also is a linear system. Oh, it's the same thing there. This is a linear system, this one, which you can see from here. This is a linear system in the unknown A0, A1, A2, and so forth. So you can see that this is a linear system. Right. So when you perform the least square, you always end up solving a linear system. Okay, that's what I want you to take from that part. Solving a linear system. So similarly here, if we substitute, we perform the least square approximation of the least square method, we end up with this normal equation. And this is a linear system. Okay? Because what do we want to find? We want to find the C's, Ci. This coefficient, C sub I. That's what we want to determine. And to determine that, we have a linear system here. Right? This is like our A. This is like our A, Ij. This is like our A, our Xj. And all this is like our Bi. You see? So this is a linear system which you can write in a matrix form. Okay, now this linear system in general is what we call a dense matrix. A dense matrix. So in this expression, this expression 128, which can be rewritten like this. N plus 1 equation in N plus 1 unknowns, right? So it's a linear system. You see? So this is the coefficient. You can see that this in general is dense. In general is dense. Now, the purpose of this section, when we are choosing Chebyshev polynomial, for instance, right? Because it's not the only one, is for us to make sure that this system, this linear system, the matrix A is not dense. So in general, A is dense. So the matrix A is dense in general. What does that mean to be dense? Dense as determined as the the word portrays, dense means that they are more non-zero elements. That's what it means to be dense. Most of the entries of your matrix A are non-zeros. That's what it means dense. So to solve a dense system or a system linear equation when the coefficient matrix is dense, it requires a lot of operations. But our purpose here is to find basis, this type of basis, because remember the G sub i's here, the G sub i's are the basis of our polynomial. So we want to select this basis in such a way that the coefficient matrix will be close to the identity matrix. Remember, if you have the identity matrix, in fact, your linear system, you don't have to solve it. You don't have to solve to perform a long linear system per se. You can see that your x, if this is identity, you can see that your x here can be found directly. You don't need to invert the matrix. If it's identity, that x gives you exactly the right-hand side. You see? Or if it's a factor of the identity, that is identity times a certain factor, you just divide the corresponding b by that factor. You see, it becomes easy. If this is close to identity or a factor of the identity matrix, then you don't need to invert. You don't need to invert the linear system anymore, or perform the Gauss elimination. You don't need that. You can read your your x, the unknown. You can read them directly, or you divide them by a certain constant term. You get the solution directly without performing the inverse of the matrix or performing Gauss elimination to solve the linear system. So that is the idea. Now, for this to be identity, what do you need? You see, what is this? This is like a dot product. This is a dot product. If you take this as a vector in Rm plus 1 and the other one another vector in Rm plus 1, this is a dot product. So if the dot product, for this to be identity, the dot product should be 1 or 0. And polynomial for which the basis satisfies that condition is called orthonormal polynomial or orthogonal polynomial. And the Chebyshev polynomial that we are going to deal with, they have this property. Okay, now let us introduce orthogonality. When the basis G sub 0 up to G sub n has the orthonormality property, orthonormality means that this dot product is 1 if I is j and 0 if I is not j. This is orthogonal when they are 0, when they are different. And when the dot product gives you 1, that is the normality, norm. It means that the norm is 1. We call a system that is orthogonal and each element of the basis, the norm is 1. We call it orthonormal basis. And the property, such a property is called orthonormality property. Right. So if these are orthonormal, obviously this coefficient will be identity. It will give you identity matrix. And there's no need to invert. We can get our unknown Cj easily. Right. So that is the purpose. You can see that we can get our, because this will be 1, and the other term will be 0, so you get your Cj directly equal to the right-hand side, which is the case here. Right? It reduces the operation. Severely, tremendously reduced. Right. Okay, the Gram-Schmidt process, I will skip it for now. And I will go straight to Chebyshev polynomial. We are going to define what it is so that before you sleep today, you will not sleep with the test of something that is not achieved. I want you to go back being happy. It's as if somebody comes with mangoes show you the mango. You see. Or the person is eating the mangoes, brings the mangoes close to your mouth. You open, you want to bite it. The person, no, 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 please. Tomorrow you eat your mango. No, man, you will not be happy. You might even slap the person, but I'm not asking you to slap anybody. So I don't want you to slap me, maybe even in your heart. I don't want you to slap me in your heart. I don't want you to go back with that unachieved test. Okay. Eat your mango now, so that you will sleep nicely. You will not have nightmares. Polynomial Chebyshev is haunting me. Because what is it? No. Okay, Chebyshev polynomial. We are going to define it. Okay, Chebyshev polynomial, first of all, it's a set of polynomials written in this form. So this is the Chebyshev polynomial of the first kind. This is called Chebyshev polynomial of the first kind. So this is how we defined it. So it is defined this way. Let me rewrite it properly here. Tnx is equal to cosine n times cosine inverse, right? Or argument cosine inverse x. So this is Chebyshev polynomial of the first kind. Of the first kind, because there's another one of the second kind, but we are dealing only with the first kind of the first kind. Okay, so that is it. That is how it is defined. But these are polynomials. Be careful. It's not because we are using cosine that we think that they are trigonometric. Actually, of course, trigonometric because it's cosine of something. But if you expand this expression properly, you will see that they are polynomial. You can even see here. If you take this n to be 0, obviously cosine of 0 is 1. You have 1 here. And if you take n to be 1, if I put 1 here, cosine inverse, that is, I apply a function to its reciprocal, it gives you identity, so that would be x. Now, if n is equal to 2, then you can use some property like this one. This identity, right? If you use this identity, T2 will give you this one. So Tn, in fact, is an n-degree polynomial. Even though you write it in terms of cosine, it is a polynomial indeed. It's a polynomial. And the advantage also is that you can use trigonometry. As you can see here, we use trigonometry to generate this recursion formula, right? It is expressed, it's a trigonometric function. Yes, let's say it's trigonometry, but they are polynomials. N-degree polynomials. It can be written in the general form of a polynomial, and you can see it here. They are polynomials. And they have some trigonometric properties. That's the advantage also. Right. Okay, now orthogonality. Here is orthonormalities. They are not norm, but they are orthogonal. You don't have one, you have something but not one, a constant, right? Which you can make, or you can also make orthonormal by dividing by this non-constant term to get one. Okay, so this is the dot product, or you call it scalar product if you want, of Tn and Tm. This is how we defined it, right? So you can see that when n is not m, it is 0. So this is orthogonality. This here is orthogonality, this one. But now, when m is equal to n, you can see that they give you results that are different from 1, right? So there will be a factor times 1, factor times 1. Now, if you want to make it orthonormal, for each, when m is equal to n equal to 0, you have to divide by pi. When m is equal to n, but not 0, you have to divide by pi by 2, so that this becomes 1, 1. And I have the orthonormality property. But we don't need orthonormality because this is enough. The fact that when m is equal to n, you have a constant term, it is still similar to orthonormality because you just have to divide the term by pi or by pi by 2. You still have similar result. So this is how you define the orthonormality property of Chebyshev polynomial. You can see that they are orthogonal. So they can help us if you use them as a basis to obtain something that is close to identity and solve this normal equation easily. So for some cases, you will get, in fact, you get this divided by pi or by 2 by pi here. Because here you have the factor of pi or pi by 2 here. You just divide. So you see have something of this form, which is a simple expression. Okay, so I will stop here for today, and we will continue tomorrow. Is there any question or any concern before we stop? Is there any question, any concern? Okay, if there's no question for now, you can keep your question for tomorrow. You are having another class after this, surely. I think so. Okay, we'll stop here. Thank you for your kind attention. God bless you and see you tomorrow afternoon. Bye-bye.
Bye.